Yeah, so last time we were looking at linear programming, and we had this optimization problem. So, basically you have a system of linear equations, but you assume that all the variables have to take non-negative values, and you have this objective function C transpose x, and you have to maximize it. So, we have seen that a whole variety of different problems can be brought into this form, right. Your original problem may have inequalities, but then by adding slack variables, it may also have negative variables. So, you can somehow make them positive. It might have variables with no conditions on their sign. You can separate them into two non-negative variables. So, this is the standard form that we assumed, and then we sort of I explained how you can set this up in terms of something called a tableau. So, let us just see that again. So, here was a problem that we started with, maximize x 1 plus x 2 subject to the conditions x 1 plus x 2 is less than or equal to 1, x 1 is less than or equal to 3, x 2 is less than or equal to 2. And then we had x 1 greater than or equal to 0, x 2 greater than or equal to 0. So, because these were all inequalities, this, and this, we just added 3 slack variables x 3, x 4 and x 5, and so we were able to kind of, by increasing the number of variables, we are able to put it in standard form. And in this case, because of these slack variables, there is a obvious sort of basic feasible solution where you take these slack variables to be the basic variables. So, we set up the problem in terms of nice visual table, which we call a tableau. So, we write down the basic variables here, and because the submatrix corresponding to the basic variables is non-singular, you can express the basic variables in terms of the non-basic variables. So, so I hope that part is clear. So, maybe I can explain this in terms of block matrices. So, let us just so we have this matrix A, and let us just move all the basic variables to the left and the non-basic variables to the right. So, let us say, so B is a subset of 1 to n, and let us say B bar is the complement of B. Okay, so you can write your x as a column vector with two parts, x b and x b bar. So, you just write all the basic variables on top and your non-basic variables at the bottom, and then this system of equations, and I will also take the matrix A and write it as two submatrices A b and A b bar. So, this system of equations, you can separate out the basic and the non-basic variables, right, and then this is equal to B, right. So, what this equation here is saying is that how do I, so what do you have? So, you have A b x b plus A b bar x b bar is equal to B, and this allows you, now you can write x b as A b inverse times B minus B minus A b bar B times sorry A b bar B x B bar. sorry, x b bar. I will write b minus a b bar x b bar. So, a b inverse, okay. A b bar x b bar. So, there are the b variables and the b bar variables, right, and we have a x is equal to b. So, that means a x a b x b plus a b bar x b bar is equal to b, right. So, that means x b is equal to a b x b is b minus a b bar x b bar. So, x b is a b inverse times b bar minus, oh, this thing is not there, this is not a b bar, this is a vector b, okay. So, yeah. I thought you were saying this b bar here will not be there, okay, great. So, that's what's happened here. So, we have written the basic variables in terms of the non-basic variables. And we have also, because you can express the basic variables in terms of the non-basic variables, you can also express the objective function entirely in terms of the non-basic variables. So, if the objective function had some basic variables in it, then you could remove them because you have formulas for the basic variables in terms of the non-basic variables. And so, this is a tableau, and at a glance it sort of tells us where we are in this optimization problem. So, now when you look at this tableau, you see that there are this x 1 and x 2 both have positive coefficients, which means now in the basic solution, which was this 0 0 1 3 2, x 1 and x 2 are said to be 0. So, the basic variables are said to be 0. Using this, you can compute the non-basic variables, and you will just get this first column here of this tableau, the constants, the column of constants. And so, now what this here tableau tells us, that if I were to increase one of x 1 or x 2, I would be able to increase the value of the objective function. So, you pick one of them and you try to increase it, and so in this case I picked x 2 and tried to increase it while keeping x 1 equal to 0. So, what happens now is I try to increase it, but each of these equations in the original tableau, since these basic variables in the older tableau have to be non-negative, gives me a constraint, possibly gives me a constraint on how much I can increase x 2, right. So, x 1 is going to be 0. So, this says 1 minus x 2 has to be greater than or equal to 0, which means x 2 has to be less than or equal to 1. The second condition gives me no condition on x 2 because it does not the second equation, because it does not involve x 2. The third equation also gives me the constraint that x 2 is less than or equal to 2. So, out of these two constraints, the stronger constraint of course is that x 2 is less than or equal to 1. I can't increase x 2 greater than or equal to 1 because that would make the variable x 3 less than 0. However, increasing x 2 to 1 makes the variable x 3 equal to 0, and so I can think of that, I can try to make that a non-basic variable because its value is 0, right. So, I will move x 3 to the non-basic side and I will move x 2 to the basic side, and so so then after you do that, this is what you get. So, let me just copy this and we will just run through this example because it's helpful in understanding what. So, on the one hand there is the practical side of linear programming, and we will also see that the theoretical side, the fact that this algorithm runs and works, has some interesting implications. So, let us just take this. So, this is our tableau now, and now you see that what can I do, which of these variables can I increase? Only x 1, because if I increase x 3, then the objective function will go down. So, maybe we will probably end up going back to the previous tableau. So, let us try to increase x 1. Okay. So, I will try to increase x 1. So, and what you get? So, we will keep x 3 equal to 0. So, you get 1 plus x 1 is greater than or equal to 0, which is saying that x 1 is greater than or equal to minus 1. That is not a constraint, because anyway we have assumed that x 1 is greater than or equal to 0. But the second one tells us that 3 minus x 1 is greater than or equal to 0, which says that x 1 is less than or equal to 3. And the third condition tells us that 1 minus x 1 is greater than or equal to 0, which means x 1 is less than or equal to 1. So, I can increase x 1 to 1, and which variable will go out? X 3 will go into the basic set, x 5 will go out, because that is the variable that has become 0 now, right. So, now I must have my new basic variables are x 2, x 3 and x 4, x 5 has gone out. So, let us write them down. So, x 3 I can write from here in terms of, so x 1 and x 5 will be on the right hand side. So, x 3 is minus 1, right. Is that right? No, yeah, x 3 is, no, x 3 is what am I doing here? So, x 1 has gone out. Oh no, I am bringing x 1 in, not x 3. So, x 3 is kept to be 0, sorry. So, x 1, x 2, x 4 and x 5 has gone out. So, now this x 1 I can put, I will use equation x 5 is allowed to be used on the right hand side. So, I will use this third equation. So, x 1 is equal to 1 plus x 3 minus x 5, right, and x 2 is equal to, now what do I have to do? This x 1 I have to replace by 1 plus x 3 minus x 5. So, I will write it as 1 plus x 3 minus x 5 minus x 3. So, this becomes 2 plus x 3 minus x 3 cancel. So, 2 minus x 5, 2 minus x 5 and right, I hope I did that correctly, 1 plus x 4, oh yeah 4, but why do I have x 5 here? Yeah, so x 5 has to be here, right. Sorry, x 2 is 1 plus x 1 minus x 3. Oh, okay. So, what's wrong with this?
No, you said x 5 in the third one. X 4 should be like third.
Oh, 5 has gone out. Yeah. Sorry. So, x 4 here. And this I was just hoping, I hope I have done this correctly, just and then the last x 4. So, x 4 is 3 minus x 1, but I have a value for x 1. So, it is 3 minus 1 plus x 3 minus x 5, which is 2 minus x 3 plus x 5, right. And the objective function also needs to be rewritten. So, this is now, so I have 1 plus 2 into and then we have x 1, which is of course 1 plus x 3 minus x 5 minus x 3. So, this becomes 3, then what is the coefficient of x 3? 2 x 3 minus x 3. So, it becomes plus x 3 and then it is minus 2 x 5. So, 3 plus x 3 minus 2 x 5. So, you see now the basic solution is, what is it? So, x 1 is 1, x 2 is 2, x 3 is 0, x 4 is 2, x 5 is 0, and the objective function has attained a value of 3, which is a better than the 1 we had. So, now you see there is still further scope for improvement, because the coefficient of x 5 is negative, the coefficient of x 3 is positive. So, if I to increase x 3, then I will be able to do it. So, let me just finish this off. So, you will see a complete example. So, last pivot step, and so what I will do is try to increase x 3, and now I can probably go a little faster if you help me out. So, increase x 3 while keeping x 5 equal to 0. So, the first equation becomes 1 plus x 3 greater than or equal to 0, which gives no constraint. The second equation gives no constraint either, it is only the third equation that gives a constraint, 2 minus x 3 greater than or equal to 0, which means x 3 is greater than or equal to 2. So, we want to increase x 3 to 2, x 4 becomes 0. So, now our variables are x 1, x 2, x 3, right. So, and x 3 we can express in terms of x 4 and x 5 just by doing 2 minus x 4 plus x 5, right. And now we can use this to remove x 3 from the other equation. So, well, this never had any x 3. So, we are fine here. This one is 1 plus 2 minus x 4 plus x 5 minus x 5. So, this becomes 3 minus x 4, that is it, right. 3 minus, see I am getting better at it now, and z is, so now again we have to do 3 plus 2 minus x 4 plus x 5 minus 2 x 5. So, this is 5, see further improvement, minus x 4 minus x 5. Okay. So, look at this tableau, and can we just by looking at this tableau conclude that we have achieved optimality. So, what is the basic feasible solution? We have the basic feasible solution, I will now call it x star, but actually it turns out to be optimal. X 1 is 3, x 2 is 2, x 3 is 2, 0 0, and C transpose x star is equal to 5. So, now in this solution x 4 and x 5 are said to be 0. The objective function is written entirely in terms of x 4 and x 5, right. So, if I were to increase x 4, if I were to look at any other feasible point, it would have x 4 and x 5 greater than, at least one of them would be greater than 0, and the objective function would actually decrease, right. So, what would happen is that this so this clearly just from this tableau we can see that this has to be optimal, right. So, this is optimal because all the non-basic variables these coefficients are negative, have negative coefficients. So, because the I should say, to be precise, I should say the objective function in terms of non-basic variables has negative coefficients. It is enough if it has non-positive coefficients, even if the coefficient is 0, then of course changing it does not matter, and you could perhaps increase that variable and get more optimal solutions, but you just want one optimal solution. So, negative, but it is enough to say non-positive coefficients. So, any other feasible point would have these things positive or at least one of them positive, and the objective function would go down. So, at least it cannot go up if they are all non-positive, right. So, So, not only does the simplex method help us to compute the find the optimal value, but it also shows us that that value is optimal. It gives us a proof, right. And there are certain subtleties to running this simplex method. So, we made in these, so these are called pivot steps, and in each pivot step we made a choice of a variable. And sometimes you will see that you have many choices of variables, and then you have to decide how to choose it, and some issues can occur. I will not go into the details, but there are possible difficulties, like you might start going around in circles without really improving the uh, objective function, or so, but there are pivot rules. So the important thing about implementing simplex method algorithm is to choose your pivot rules. So, there are many different pivot rules. One is, for example, you look for the one of the coefficients, the variables with the largest coefficient. So, for example, here suppose you had 2 x 1 plus x 3, then you would pick x 1 because it has the biggest coefficient. So, if you just increase it slightly, the objective function will increase a lot. But then you might want to say, okay, I can't increase x 1 too much. So, let me also look into how much I can increase it. You could use that as a criterion for choosing which variable, and then you have to have some rule for tiebreakers and so on. But there are, so it is a theorem that there are pivot rules with respect to which this algorithm will always terminate, provided there is a optimal solution. So, whenever there is an optimal solution, this simplex algorithm, if implemented using a carefully chosen pivot rule, will terminate. And so, you will end up with you will always end up with this kind of a tableau, where the coefficients of the non-basic variables are non-positive, and at that point you will have found an optimal solution. So, this is sort of briefly how the simplex method works, and there is a beautiful reference, it is by Matusek and what is the other guy's name? Yeah, I forgot the other guy's name. Okay, I'll send it to you in the drive. So, yeah. So, okay. So, let me just formalize this a little bit, in the sense what is a tableau exactly, and how do you find the various components in a tableau. So, here is the structure of a tableau. So, at each stage, so you have variables 1 to n, and at each stage you have some b. So, x b, so b is a subset of the set of variables, basic subset, and I will write x as, there is one more thing I did not mention, is how do you get started in the simplex method, right. So, we had this other example where we are having trouble finding a basic feasible solution. So, I will also talk about that, but let me just tell you what a general simplex tableau looks like. So, we are going to write this x as a block matrix, that is two parts, x b and x b bar. So, b bar is just the complement of x of b, and we are going to also write A as the block matrix A B bar. So, what we are saying is that A x is equal to A b x b plus A b bar x b bar. Okay. So, a simplex tableau is of the form you are going to express the basic vectors, there is going to be some column of constants plus q times x b bar. So, you are basically expressing the basic vectors in terms of the non basic vectors, and z is equal to z naught plus r transpose x b bar. So, if you look at this example here, right. So, B is 1, 2, 3. So, that means that this P, what was it? P, the vector P is 3, 2, 2, right, and the vector, the matrix Q is the matrix minus 1, 0, 0, minus 1, minus 1, 1, right. X b is just x 1, x 2, x 3, x b bar is x 4, x 5, and what else is that? Z naught is 5 and R transpose is minus 1, minus 1. Right. So, this every tableau looks like this, and we can easily compute these matrices, because we have this equation here. So, if we think about this, what are we saying? X b is I had already worked this out. So, this is equal to b. So, x b is A b inverse b minus A b inverse A b bar x b bar, right. So, what we get is P is equal to A b inverse b, Q is equal to A b inverse A b bar, that is it, no x b, x b bar is there, and what is this? Okay, so Z is C transpose X, right, but that is really, so we should probably also split up C into two parts. So, let us write C transpose as C transpose B, C transpose B bar. There are coefficients of the basic variables in the objective function and the coefficients of the non basic variables. So, we are calling them C b and C b bar. So, so the book is, I just remember the second author's name, Matusek and Gartner, and title is something like Understanding and Using Linear Programming. It is a very nice book in the sense it is sort of very appealing to both practitioners who want, people who want to use linear programming for applications, and also to mathematicians who want to understand the theory behind it for other purposes, like well, we use these things in combinatorial problems too. So, yeah. Okay, so let us come back. So, now what is R? Okay, what is Z0? So, this is C t b x b plus C t b bar x b bar, right. And now we have to just remove this x b and put in x b bar. So, we know how to do that. This is C t b, x b is anyway this A inverse b b, right, minus A B inverse A B bar plus C T B, and this, oops, maybe I should do it let us just give ourselves some more space. Let us make this a plus here, this times x b bar. Did I do that right? So, what I get is z naught is C T B A B inverse B. So, this is the part that does not depend on x b bar, and R transpose is something is off here, no? There is a C T and there is a C T B to the left. So, let me just write it as this C T B bar minus C T B, and then have to put the value for A B inverse A B bar x B bar. I hope I did that right. C T B minus C T B A B inverse A B bar, and there is no x B bar here, because because x B bar is outside the thing. So, that's the, these are the formulas for. So at any stage the tableau can be described entirely in terms of the original variables and so on. So, these are the formulas for the tableau, and the final tableau will have the condition that R T prime is less than or equal to 0. Okay. So, now let me just mention how to get started, how to begin how to find at least one basic feasible solution. So, maybe it is best to do it with an example. So, let us say we have a linear program already put in equational form, something like z equals x 1 plus 2 x 2, that is your objective function. It does not matter now, because we are only looking for a basic feasible solution. So, we will just start with some equations, 3 x 1, 3 x 2 plus x 3. And 2 x 2 plus x 3, what, no there is no x, sorry, I jumped ahead of myself. Let us just say the problem is this, and 2 x 2 plus x 3 equals 2, and let us say we have the condition, the usual, x 1 greater than or equal to 0, x 2 greater than or equal to 0, and x 3 greater than or equal to 0. So, now I want to find a basic feasible solution for this, right. So, it may not exist or it may exist. So, what I do is I add some variables which measure the gap from feasibility. So, I want x 1 plus 3 x 2 plus x 3 to be equal to 4, but maybe it is not equal to 4. So, let us put that gap, I will introduce a variable for that. So, let us say x 1 plus 3 x 2 plus x 3 plus x 4 is equal to 4. Okay. And certainly, if I start with 0 0 0, then this thing will be less than 0. If I put x 1 x 2 x 3 all equal to 0, then this x 1 plus 3 x 2 plus x 3 will be 0. So, I can also assume that this x 4 is greater than or equal to 0. And similarly, for the second equation, I introduce a new variable which measures the gap. So, I will take 2 x 2 plus x 3 plus x 5 is equal to 2. And now, I will take x 1, x 2, all the variables greater than or equal to 0. So, now, and what should I do now? So, this objective function is sort of irrelevant at this stage, right. Let us not worry about this, because we are just looking for a basic feasible solution. So, what should we use as an objective function here? So, I want to see if I can make x 4 plus x 5 0, right. So, let us just use minus x 4 minus x 5. So, let us say maximize minus x 4 minus x 5. So, this is called the auxiliary program. And so, you start with your program and you construct the auxiliary program. Now, you use the simplex method. In the auxiliary program, these gap variables, right, these are already sort of basic, right. I mean, I can take them as basic, because x 4 and this block of the matrix. So, the matrix is 1 3 1 1 2.
Hello, sir.
Yes, yes, please.
Sir, could you please explain again this maximize part, how it is coming minus x 4 minus x 5?
Right, right. So, the thing is, I want to know if I can make x 4 and x 5 0, but x 4 and x 5 anyway I have said should be greater than or equal to 0, because these right hand side values are non-negative. Actually, the right hand values could be negative also. If they were negative, I would just multiply the entire equation by minus 1 and assume that they are non-negative. So, these right hand side values are non-negative. So, to start with, I know that x 4 and x 5, if there is a feasible point, I should even if there isn't, there is a feasible point for this auxiliary program with all the original variables equal to 0 and the new variables being non-negative. So, now suppose, yeah.
Sir, here x 4 and x 5 are the artificial variables?
Yes, they are auxiliary variables. So, I introduce them as an aid to finding my feasible point. Now, suppose the original program. So, let us call this program P and let us call this program P prime. Now, suppose the program P has a feasible solution. What does that mean about? That means that the program P prime has a feasible solution where x 4 and x 5 are both 0, and I need to find that solution. Okay. And if P prime does not have a solution where both x 4 and x 5 are 0, then P is not feasible. So, whether P prime has a solution with x 4 and x 5 equal to 0 is equivalent to P being feasible, having a feasible solution. So, if I want to find out if P has a feasible solution or not, what I will do is I will set up this P prime and try to maximize minus x 4 minus x 5. Now, this will necessarily be, yeah.
So, if there were inequations in our original program,
sorry?
First we have to inequations, I mean inequalities. Then we have to use the slab variables.
Yeah. Yeah, so I am assuming we have already done that and our program is So, now we are introducing even more variables, right. So maybe our original program had some inequalities, we introduced slack variables and got it in equational form. And now to check the feasibility, we have to create an auxiliary program in which we introduce even more variables, and these are the sort of gap, the how far you are from feasibility. And now you try to maximize minus 4, minus x 4, minus x 5. If you maximize this and still get an optimal value which is strictly less than 0, then you will conclude that the original program does not have a feasible point. So, if the maximum value of the objective function for p prime is negative, then p does not have a feasible solution, does not have a feasible solution. If the maximum value for p prime is 0, then you take that feasible solution, it will also be a feasible solution for p. Then the optimal solution, any optimal solution, for p prime gives a solution for p, because you just ignore those extra variables which are 0. Okay, so yeah, I hope this answers your question and has made matters somewhat clearer. So here anyway these auxiliary variables will always be basic, because that part of the matrix, oh yeah, I was saying that. So if you look at this matrix, it looks like this, 0, 2, so this auxiliary part is always the identity matrix, and if you set those auxiliaries, if you set the all these variables to be 0, the auxiliaries will just have values equal to the right hand side. That is very far from being feasible for the first. So in some sense you are starting with 0, 0, 0 for p, which is not feasible. So you are introducing these auxiliary variables to see how far it is from feasible, and then you are trying to reduce them. If you can reduce them to 0, 0, then you will get a thing. So to start this program, there is no problem, just use the auxiliary variables as basic in the first step. So that's the basic idea about getting started, right. So now we know how to set up, how to get your first tableau. So maybe we can do this today as a exercise. Take this program p and use this method to find, because this is only 3 variables, so you could probably easily guess, but let us just use this method to find out if this has a basic feasible solution or not, which is the same as saying whether it has a feasible solution or not, and let us see what we get. So, yeah.
So, this way of constructing will let the other variables to be always positive, that is what we are saying, because in the previous class we had the problem.
Sorry?
In the previous class also we found the basic variables, but when we are trying to estimate the other variables we got the negative values, that is why we shift back and then.
Yeah, so in this second program also we have said that all the variables are positive, or rather are non-negative. And the initial basic variables, putting x4 and x5 as basic variables, they are also non-negative, because as I said, suppose the right hand side here is, suppose the right hand side here were negative, we would just multiply the entire equation by -1 and make it positive. So we will assume that these right hand side things are non-negative to start with. So initial values that you would put for these auxiliary variables will always be non-negative. So you are starting out with a basic feasible solution. So there is no worry there. So always you are starting out with a basic feasible solution. And so then you can, and once you start out with a basic feasible solution, the way pivoting is done, it ensures that you still have, once you start with the basic feasible solution, the way pivoting works is you will always end up with another basic feasible solution, because you are increasing the variable only to the extent that is allowed by, without making any of the other variables negative. So you will stay within the feasible set. So you just have to get started, and here there is no trouble with getting started because of the way this whole thing is designed, this algorithm. So you can find your first basic feasible solution and then go on. This is actually important because in practical examples there could be hundreds of variables, and so the number of subsets of a set of size 100 of say size 40 is some huge thing, right. So you say you have 40 equations and 100 variables, then 100 choose 40, there is no way you can start trying them randomly and looking for it or exhaust them all. So you have to, I mean, in that sense, if you could do that, then you could even solve the whole optimization problem by taking all the possible B's, checking if they are feasible, then computing the value there, and so we do not want to do that. Instead, we cleverly sort of start somewhere and move towards the optimal solution by increasing variables in steps. Now, the number of steps involved could also be large, and so this whole process of how to do it depends on how you choose your pivoting rule. So it is usually run as a computer program, so there is no human judgment involved, and so you have to give a rule, it is an algorithm, what is the pivot, which variable should I try to increase, and that is called a pivot rule. And so there are different pivot rules which have different nice features. There is one called Bland's rule, which makes sure that you reach an optimal solution in finitely many steps, but it is not always very fast. And there is also a difference between sort of practical applications and theoretical applications. So most practical problems where you are working with floating point and so on, there are no real issues, this thing runs very fast, and algorithms which are fast always give you the, almost always give you the optimal solution very quickly. So this is a really nice and useful algorithm for solving massive problems, and as you have seen, a lot of interesting problems, flows in networks, line, separating line, fitting line, and so on, do become linear programming problems. So okay, so one of the most amazing things about this linear programming is something called the duality theorem. So this is something which is a little subtle, and so yeah, so let me just start with an example and we will see how this works. So duality. So to motivate duality, let us start with an example and see without solving this, how can we put upper bounds on the objective function. So let us see where it is. Yeah. So let us look at an example. So maximize 2x1 plus 3x2 subject to 4x1 plus 8x2 is less than or equal to 12. This is our first equation. 2x1 plus x2 is less than or equal to 3. Let us call this equation 2, and let us say 3x1 plus 2x2 is less than or equal to 4. Okay, so this is not an equational form, and let us say x1 x2 greater than or equal to 0. So, okay, so can we say something about this objective function? So, we are assuming that x1 and x2 are greater than or equal to 0, right. So, so this 4x1 plus 8x2 certainly is greater than or equal to 2x1 plus 3x2, right. So, 2x1 plus 3x2 less than or equal to 4x1 plus 8x2, and this is less than or equal to 12. Right. So, you can see here that 12 is certainly an upper bound for this optimization problem, right. Can we do a little better? This is the objective function, right. So, what I am saying is that the objective function will never exceed 12. Can we do somewhat better than this? 6, because you can divide by 2 and still you will have coefficient wise inequality. 2x1 plus 3x2 less than or equal to 2x1 plus 4x2, which is equal to half of 4x1 plus 8x2, which is less than or equal to 6. Can we do a little better?
Into 3, the third equation into 2 minus the second one.
Okay, so let us take the third equation into 2
minus the second one.
minus then the inequality gets split. We do not want to do minus. Yeah, but your idea is good, like maybe do not just take one equation, take 2 of the equations and somehow combine them. But you can't do minus because the direction of the inequality will flip. So, so can anybody do better than 6 without solving this?
Add equation 1 and 2.
Add equation 1 and 2. So, if I add them, I will get 6x1 plus 9x2 is less than or equal to 15. So, okay, so 2x1 plus 3x2 is less than or equal to 15. Divide by, oh, divide by 3, wonderful. So what we get is 2x1 plus 3x2 is less than or equal to 5. So, we have gone from 12 to 6 to 5. So, what are we doing here, right? So, what we are trying to do is we are trying to derive an identity, something like dx1, let us say d1 x1 plus d2 x2 is less than or equal to h, where d1 is greater than or equal to 2, d3 is greater than or equal to 3, right. We are trying to derive such an identity from these equations. And what are the what is how do we get such an identity? We try to take a linear combination of these equations. So, let us say that I am multiplying the first equation by a factor of y 1, I am multiplying the second equation by a factor of y 2 and the third equation by a factor of y 3, and these are all non-negative. So, what I am trying to do is, given y 1, y 2, y 3 all non-negative, let us look at y 1 times equation 1 plus y 2 times equation 2 plus y 3 times equation 3, and that will be less than or equal to whatever this thing is, right. 12 y 1 plus 3 y 2 plus 4 y 3. And what do I want to do? I want this h to become very small, right. So, what do I get in this case? So, and I also need that this coefficient of x. So, let me maybe I need more space here. So, let us copy this thing. Let me even make it slightly smaller. Okay, so this is the problem that I had, and so when I do this, what do I get? I get 4 y 1. So, I want d 1 y 1 d 1 x 1 plus d 2 x 2 less than, I want this kind of an equation, right, and I want d 1 less than or equal to 2, d 2 no greater than or equal to 2, right, because I want to upper bound this. So, d 1 less than or equal to 2, no greater than or equal to 2. Okay, so let us see what I can get. So, if I do this, I will get so I will get d 1 is 4 y 1 plus 2 y 2 plus 3 y 3, right, and I want it to be greater than or equal to 2. That is the coefficient of x 1. So, d 1 is this, and what do I get for d 2? 8 y 1 plus y 2 plus 2 y 2, and this should be greater than or equal to 3. Thanks, y 3. And what else do I want to do? I want to minimize h, right, and what is h? H is 12 y 1 plus 3 y 2 plus 4 y 3. So, the problem becomes minimize 12 y 1 plus 3 y 2 plus 4 y 3 subject to the equation, the inequalities 4 y 1 plus 2 y 2 plus 3 y 3 greater than or equal to 2, 8 y 1 plus y 2 plus 2 y 3 greater than or equal to 3. So, we had this original linear programming problem, which is a maximization problem with these kinds of inequalities, and we ended up with a different problem, which is a minimization problem with inequalities in the reverse, and the matrix here is the transpose of the matrix here. So, yeah, so this is so if we write this program as A x is less than or equal to b, maximize well, let me just write like z is equal to C transpose x, right. So, this is the first program, we call it the primal. Primal means first. So, then what does the second program look like? A transpose y greater than or equal to C, and what should we do? Minimize. So, these 2 and 3 are these things, no? The C. Z equal to B transpose y. This is called the dual. And what we see is that because of the way we came upon this in the first place, any feasible solution to the dual is an upper bound for the primal, right. So, this is the dual, and what we see is immediately observe that any feasible solution for D is an upper bound for P. So, one immediate use of this would be to say that if you have program P and you want to know if it has an upper bound, well, you just look at its dual program and check if it has a feasible solution. So, this is the basic idea against in duality. So, what we are saying is that sometimes this is said as D guards P. Okay, but what is even more surprising? Yeah, that the minimal solution, so optimal values of P and D are actually the same. What we saw is that the optimal value of D is greater than, each feasible solution for D is greater than or equal to the optimal value for P, but now what we are saying is that the each that the optimal value of D is equal to, they are exactly equal, and this is a very nice. So, let me just state that. So, this D guards P is sometimes called the weak duality theorem, but there is this exact statement that solving D or solving P, at least you get the same optimal value. So, let us state this duality theorem in general. Sorry,
Will it be exactly same?
one sec.
Minus symbol is that page.
Oh yeah, I was using the keyboard today, so I forgot. Yeah. Okay. So yeah. So the it will always be that the maximum value for p is equal to the minimal value for d. So you don't have to worry about least upper bound and so on, because these are the set of possible values that this objective function can take. It's going to be bounded above and it's going to be closed, because these inequalities are all weak inequalities. So if there is a least upper bound, it is also a maximum. If it's unbounded, then there is no least upper bound, but if it's bounded, its least upper bound is a maximum, because the set of values taken by 2x1 plus 3x2 subject to these is a closed set, just because these constraints themselves give you a closed set. 2x1 plus 3x2 is so they is a continuous function, and so if you if it's I think so. So now if you have a sequence of points, of feasible points which converge to some probably some compactness argument can be used anyway. So just think about it. But if it's if there is a, if it's bounded above, it will have a maximum. So this least upper bound is not an issue here as far as I know.
I'm understood that the solution will exist if the D has a min solution.
Right.
But the optimal values in which the
No, I am not saying it's obvious at all. Yeah. So that requires a proof. So the fact that the optimal values are the same requires a proof. And that we will do.
yes. So it has to achieve the minimum of this program.
The minimum of D has to
be the
match.
maximum.
So you are trying to minimize this, you are trying to maximize, and finally they will come to the same value.
Yes.
So that's the duality theorem, and it's a non-trivial theorem. So the duality theorem says that, so suppose you have for the linear program, so we will call this maximize C transpose x subject to A x less than or equal to b, and x is greater than or equal to 0. So this is the primal, and the dual is minimize B transpose y subject to A transpose y greater than or equal to C and y greater than or equal to 0. Exactly one of the following occurs. So, the first possibility is, it could be that neither P nor D has a feasible solution. But if P is unbounded, what do you expect for D? So, remember, any feasible solution for D guards P, right. So, if P is unbounded, then T D cannot have any feasible solution, right, because any feasible solution for D is an upper bound for P. So, D cannot have this, we have already proved in fact. And similarly, if if P has no feasible solution, then D is unbounded. Okay, and the most interesting case is when both have feasible solutions. If both P and D have then C transpose, say feasible solutions, then C transpose X star equals B transpose Y star for optimal solutions. X star and Y star.
You're saying that D is unbounded because upper bound does not exist, or the
D will be unbounded means the lower bound, the objective function, whatever you are trying to maximize or minimize, you will never achieve that. So, D has a minimum bounded, so unbounded below.
2 and 3.
First it gives the second and third. First statement gives second and third.
The first statement, if
P is unbounded, automatically there is no feasible solution.
P is unbounded, then D cannot have a feasible solution.
In P does not have feasible solution.
P has feasible solutions, it is unbounded, so it must have at least, so the objective function for P is unbounded means there are many feasible solutions and the objective function is unbounded, right. If there are no feasible solutions, then the objective function is,
P is unbounded, the maximum is problem we are taking.
so there is no maximum, yeah.
Is that there is no feasible solution.
D may not.
No, so what is the meaning of feasible solution? Feasible solution means that you satisfy the equations Ax less than or equal to B without and x greater than or equal to 0.
So yesterday the theorem says that the objective function is bounded. Then only the basic feasible solution exists. The theorem says.
Correct. No. It says that if
there is at least one feasible solution such that the objective function is bounded,
and the objective of then there is a basic feasible solution.
then the optimal solution. Then there is an optimal solution.
The basic optimal. So that theorem, what we were saying is that if there is an optimal solution, then there is a basic. Maybe let me.
No, sir. First statement of that theorem, sir. You are saying second statement of that theorem. The first statement of theorem, if there is at least one feasible solution and the objective function is bounded, then there is an optimal solution.
Correct. Okay.
So if your objective functions become unbounded,
Then
there is no optimal solution.
there is no optimal solution, correct?
So
because it can keep getting larger
Yes,
and
yes.
larger.
So if there is no optimal solution, there is no basis.
No. The other way will not hold, right? So what will happen? So let me show you a picture of this.
Yes, I understand.
Okay. For example, your feasible region might just be between two parallel lines, and your objective function could be this, growing in this direction. So you have lot of feasible solutions. In fact, if the objective function is unbounded, that means for each real number, you can find a feasible solution such that the value of the objective function is greater than that real number. That is what it means to say that it is unbounded. So, when I am saying unbounded, I mean if it is a maximization problem, then it is unbounded above, if it is a minimization problem, it is unbounded below. So, let us also take that sort of as a thing. So, so how much of this are we convinced of? I think only 2 is clear right now, right, that if P is unbounded, D cannot have a feasible solution. But I guess yeah, but the thing is, the moment one of them has a feasible solution, the other will be forced to be bounded, right. So, this so once you take care of 2, 3, 4, 1 is the only thing that is left, that neither has a feasible solution. So, the and 2 and 3 are sort of symmetric to each other, if you can convince yourself that the relationship of duality is symmetric. So, maybe probably not enough time to do the proof of this next time, but the main thing to prove is this 4, and this is the most useful sort of this is the most useful part of this. Well, the other parts are also useful, and there are algorithms which do not just solve the primal problem, but solve the primal and dual problem together to get faster to the optimal solution, or to give you some better information about the optimal solution. Because then what you are saying is, you are not just saying that the optimal solution is greater than or equal to something, you are saying that it lies between these two values. And so, if you just want an approximation, you can just wait till these two values get close enough, and so you know at least how far you are from the optimal solution. So, you get bounds also. So, this is I mean both like practically a very useful result, and also a very beautiful aesthetically sort of result, which I always I do not know, maybe because of my poor understanding of these things, I find it quite an amazing result. So, the proof so there is a proof which actually uses the simplex method. So, what you do is you solve this using the simplex method, and then you use that to give the proof, but that proof will take some more time. So, maybe there is some few minutes left, but maybe I will stop a little earlier today, and we will do some exercise. Yeah, but if you have questions, sure.
So, any feasible solution for the primal will be the lower bound for the dual?
Yes. So, there is a certain symmetry, and that what you just said will imply that if the if D is unbounded, then the primal has no feasible solution, right?
Yes.
So, actually this argument that I did here, this you can do starting with the dual. So, we want to minimize this doing this, there's I have to think about it exactly, but so can we use these two equations to give me lower bounds for this objective function 12y1 plus 3y2 plus 4y3, right. So, for example, I could just add the two equations, right. So, here I could start with this problem now and do the same kind of analysis that I did there, right. So, there is an inherent symmetry here. So, suppose I take so I want 12y1 plus 3y2 plus 4y3, I want to bound it below now. Earlier I wanted to bound that above, but now I want to bound it below. So, maybe I could do okay. So, 12 is greater than or equal to 4, but 3 is greater than or equal to 2, but and 4 is greater than or equal to 3. So, straight away I get that 12y1 plus 3y2 plus 4y3 has to be greater than or equal to 2, and maybe I can improve it, right. Suppose I add up these two equations, then I get 12y1 plus 3y2 plus 5y3, which is certainly greater than or equal to 12y1 plus 3y2 plus 4y3, is greater than or equal to 5. So, my 2 has increased to 5, which is an even better bound, right. Oh, look, 5, this 5 and that 5. So, this 5 must be the optimal value, just in this example. Yeah. Yeah.
Minimum. And that's it.
Yeah. And in this case, we actually just land upon 5 very easily as the optimal value, right. So, now from this little analysis, we know that, this guy's minimum is 5 and it guards, this guy's maximum is less than or equal to 5, no, is less than or equal to 5, yeah, is less than or equal to 5, and this guy's and that is less than or equal to 5, this guy's minimum is greater than or equal to 5. And we also know that every feasible value here guards the other one, because it comes from taking the equations of the primal, doing some non-negative linear combination, and so it will definitely guard, right. So, just from this very simple analysis, we have concluded that this guy has optimal value 5, this guy has optimal value 5, and so 5 is equal to the optimal value 5, not optimal value 5. This has upper bound 5, this has lower bound 5. But since every upper bound here is a lower bound for this, every lower bound here is an upper bound for that, not every lower bound. Every value here is an upper bound for this, and every value here is a lower bound for that, and these are equal. Both must have optimal value 5. Right. So, somehow this looking at this dual program has given us some very nice insight into the primal. And this we will see how to dualize more general programs. So, not all programs will be in this form, maybe some variables are, but I guess you could convert any program into this form. So, you can ask, suppose I have equations, how do I dualize? But if you have equations, so you could say that this is less than or equal to 12 and this is greater than or equal to 12. And then the thing that is greater than or equal to 12, you could multiply by minus 1 and make it less than or equal to minus 12 or something. So, the fact that I have chosen it in this Ax less than or equal to b form is not really a restriction. Every linear program, just as I said, can be written in equational form, it can also be converted into this form. And then you dualize this and then reconvert it back to whatever form you like, and see what you get. So, if it is in equational form, the dual will also be in equational form, and it's not very difficult. So, I will do that maybe next time in more detail, and we will also prove the duality theorem. So, yeah, so that's it for now.
In any case, the simplex method will fail.
So, when you say simplex method, the question is with the pivot rules.
Yes.
Some pivot rules will fail. The Bland's rule will always work, but the thing is, it is very slow. So there is a tension between having methods which are fast in the average case and methods which never fail. So, in practical cases, we use algorithms which are fast. In theory, you might want to use an algorithm which never fails, but there are these things called interior point methods. So, in an interior point method, you do not go to the basic feasible solutions, you look at solutions that are inside the. So, usually this thing can be visualized as some sort of shape, and you are jumping from corner to corner in the simplex method. But in an interior point method, you do not do that, you sort of move in the interior of this polytope, and then in the last step you sort of go to the nearest corner. So, this interior point method is the best of both worlds. It works fast and it always gives a solution. So, this is due to Karmakar and is sort of the optimal thing, but the simplex method does not give that. But in practice, we implement the simplex method. The problems with the simplex method, the cycling or moving, all those things, they do not matter in practice. If you get into some sort of cycle, you just deform the problem a little bit and it will come out of the cycle. So, So, in real life things where these are real numbers and so on, these problems will not really occur, and a lot of implementations do not bother about such issues. So, yeah.